So this is our third lecture on just basically gas turbines for power plants. Basically covered the Brayton cycle, regeneration, reheat, and intercooling. Last time you have a intercooler we introduced, and so you're focusing on getting the pressure as high as possible at state 2 coming into that combustor on the high pressure side. And that's good for performance. If you do it with one compressor, maybe you have a pressure ratio of 12 or 15 or 18, it'll come out quite hot. And because it's hot while it's being compressed, it's more expensive to compress. That's a kind of an interesting concept. Liquids were incompressible, and so you could boost the pressure a lot with the liquid. But as you boost the pressure of a gas, it gets hot and it wants to expand and becomes more expensive to continue to compress. We saw that by taking and reviewing section 613. It was a very difficult, challenging section at the end of chapter 6, but it talks about the heat transfer and the work in internally reversible steady flow processes. So I have a system. Here it would be a compressor, and I'm bringing gas through that compressor and I'm compressing it. You could talk about if it's internally reversible, that's going to be maximally efficient. You have the heat transfer per unit mass is an integral TDS. We reviewed the temperature entropy diagram, maybe from inlet state 1 to outlet state 2, went from here to here or something, from 1 to 2 along this path, and the area under the curve was the representation of Q dot per M dot int rev. Then there's 3 equations for work. Now, this equation we use a lot when we have an incompressible substance. We used it in the previous chapter. Do you recognize VDP? Yeah, and so that was for a pump. But the same, it comes from the more general equation right here, where we have the integral of VDP. It just is, V is constant, it comes out that integral, and there you go. And often we neglect changes in kinetic and potential energy. So this is the one we really want to focus on. The focus is on integral VDP. And I think I mentioned the first time you see that in Thermo 1, you say there's a typo in the textbook. Because I learned, you learned, we all learned integral P dV. It's like this needs to be switched. Remember that? But it's not. It's correct. It's not a typo. It's the integral VDP. I tried to do a quick summary or the derivation of that last time. And the summary or the derivation is covered in 613. I encourage you to read that, okay? Review that. But on a pressure volume diagram, if you're going from low pressure, large specific volume at state 1, that's coming in, you're compressing it. It's typically the high pressure outlet. It's more compressed, lower specific volume, state 2. Then the area not under the curve, but to the left of the curve is a visual representation of the work per unit mass, assuming internally reversible. That's a key concept. A lot of times I'll explain it and I'll say, okay, look at, you're used to having on the abscissa, the horizontal axis, the x-axis. You're used to having something that you then have on the ordinate or the y-axis, a function f. So you write f as a function of x, right? And then you learned how to integrate f dx. You really never did the integral of x df. I mean, that's just super confusing to students. So you have the horizontal axis. So if you want, go ahead and flip this axis so that it's on the x-axis or the abscissa. Makes a lot more sense. And then you have the y-axis, not being y, but being v. And then you'll have to work a little bit. You'll have 1 over here. You'll have 2 over there. And now, sure, it's the area under the curve, but nobody, I mean, it's so confusing. Are we talking a PV diagram or a VP diagram? If you want it to look familiar like you're coming out of calculus, where it's the integral f dx, then you really want to plot it on the VP diagram. But I've never seen a textbook, a thermodynamics textbook, actually show a VP diagram. They always show a PV. All right? But there's no law against switching, so there you go. So if you look on for ideal gas, if you're going to compress it, remember we have, let's say, isotherms. So this is temperature high, temperature low, and we're going to compress. This is a PV diagram. If you compress isotropically, it'll actually jump to a higher temperature, a higher isotherm. We saw that when we studied the Carnot gas power cycles. And this would indicate that you have quite a high work per unit mass, a large area. But if you could compress it while it stayed the constant temperature, can you see that you'd have a less work per unit mass? It'd be cheaper. You'd achieve the same pressure increase, but it would be less work. You have to think about that for a minute. I can achieve the same goal of having a higher pressure, the same pressure increase, but it'll cost me less mechanical work in driving that compressor? Yes, that's exactly it. But nobody really makes a compressor which is a great heat exchanger at the same time. It's compressing and cooling at the same time. So what do? They say, I can make a good compressor that's not a heat exchanger, and then I can make a good heat exchanger. So what I'll do is I'll compress isentropically some of the way. I'll then stop it at this intermediate pressure. I'll cool it back off to the same temperature I had before, and then compress the rest of the way. Oh, it won't be as efficient as isothermal compression of an ideal gas, but I can't really do that. I mean, engineer can struggle with that. I've seen people propose that. I've seen people write papers on that. I've seen people study it. I've never saw it in practice. You have a compressor, then you have a heat exchanger, right? All right. So here you could see now that this area under the curve, or to the left of the curve, I should say, is there. So what is the savings? It's this hatched area, which is a visual representation of W dot per M dot saved, reduced, less work per unit mass. All right. Wow, these problems get long, don't they? Let's sort of try this problem. So we have an air standard regenerative Brayton cycle. So right away, Brayton, we're going to have a compressor, a burner, a turbine. Regenerative, we're going to have a regenerator in between. So here's our compressor, then we're going to go to a regenerator, then we'll have a burner. Sometimes I call that a combustor. And then we're going to eventually get to a turbine. Let's continue to read it. Operate steady state. All of our cycles in this chapter operating at steady state. There's no transients, start up or shut down. It has intercooling. Right away, key word, intercooling. It's trying to be more efficient with the compressor. So I'm going to have two compressors, compressor 1 and compressor 2, and I'm going to have an intercooler right here. So the air is going to come into that first compressor, come out of it, go through the intercooler, be cooled at high pressure or the intermediate pressure, then go to the second compressor and finally get to the highest pressure. Okay, that's the intercooler. And it has reheat. Oh boy, so I'm not only going to have one burner, I'm going to have two burners. And that means I'm going to have one turbine and two turbines. Two stages, maybe they're all in the same package, but two stages of the turbine. So after the first burner, you go to the first turbine. After the first turbine, you go to the second burner for reheat, and now you're ready to come out. After this, we're going to come back, cool those exhaust gases in that regenerator, and they never really show it completing the cycle, but you need to complete the cycle, so put in some heat exchanger to complete the cycle. Now I can account for all the heat in and heat out, work in and work out of this cycle. So, all right. The cycle produces 10 megawatts of power. Is that net power or just the power out of the turbines only? It'll be net, meaning that some of the power out of the turbines has to go back and feed the compressor. So you have to take that off. And so it's the net. Normally we work with a cycle where we're calculating lowercase w net, specific work net, right? How is that related to w dot cap net? Mass flow rate. What's the mass flow rate? It's the mass flow rate of the air going through each of those components through the cycle. That's the mass flow rate. That's a bad looking mass flow rate. Let's try it again. There. Okay. So it's 10 megawatts of power out of the cycle. Air enters the compressor 1 bar 300 Kelvin. So they're telling us right down here at state 1, the P1, T1. The first compressor pressure ratio is 3. Can you tell me if this is state 2, what is the pressure at state 2? If that first compressor pressure ratio is 3, what's the pressure at 2? 300 kilopascal or 3 bar. 3 bar, maybe I stay in bar. 3 bar, true? What's the pressure coming out of the intercooler? What's the pressure at state 3 right here? 3 bar. All right. Let's continue to read. The second compressor pressure ratio is 4. So let's say this is state 4 right here. What is the pressure at 4? It's 12 bar. True? Walk around. This is very consistent. Get all your pressures right. Then worry about your temperatures and then your works and heat transfers for each component. All right. Let's number our states. Let's call this state 5. Let's call this state 6. I know that they introduced X and Y and A and B and then C and D. Boy, there's a lot of... But then later in the chapter, they just renumber all the states as well. So when you're solving a problem, I'll be able to figure out if you clearly label your states, what names you're giving or numbers you're giving. So that's state 6, that's state 7, that's state 8, that's state 9, this is state 10. Do I have any other unique states? Should I have maybe only 7 or 8 or 9 states, or is 10 the right number? Or maybe I need 11 or 12 or 14. Is this the right number of states? Yeah, it is. It'll take you longer to make that decision, but you do need to grapple with that, struggle with it. Okay, let's continue to go through. So the first turbine pressure ratio is 4. So what is the pressure at 5? What is the pressure at 6? What's the pressure at 7? What's the pressure at 5? It's still 12 bar. What's the pressure at 6? 3. Pressure at 7? 3. It's still, yeah. Then you go through the burner. The pressure at 8 is 3. Now, finally, the pressure at 9 is 1. 1. What's the pressure at 10? 1. Okay. So we get our pressures right. The intercooler cools the air to 300 Kelvin. They're telling us the temperature at 3 is back down to 300 Kelvin, just like the temperature at 1 was 300 Kelvin. The intercooler really brings the temperature down. Yes?
Why is pressure 6?
Oh, it's not 3. It's 12. Thank you for the correction. It's 12, correct? Yeah, thank you. Okay. The air temperature after each combustor is 1400. So the temperature, well, that's 1450. Temperature at 6 is 1450 Kelvin, and the temperature at 8 is 1450 Kelvin. After each of the burners or combustors, okay. The isotropic efficiency, boy, after you solve a few of these problems, you just don't like to read certain words, do you? I don't. You got to be kidding me. This is going to be a long problem. Isotropic efficiency of each compressor is 85%. Same here, isotropic efficiency is 85%. And then for each turbine is 95%. So the efficiency of the turbine 1 is equal to the efficiency turbine 2 is 95%. And the regenerator effectiveness is 80%. This is a long problem. Assume ideal gas behavior with constant specific heats. So basically a cold air standard analysis. Determine mass air flow rate. Well, that's this one. How are we going to calculate the mass air flow rate? There's no easy way. It's a lot of work before you get the answer to part A. Basically, I need to get this. And how do I get the specific work net for the cycle? Work net of the cycle is what comes out of turbine 1, what comes out of turbine 2, what comes out, and I'm going to put it compressor 1 because it's going to be negative, what comes out compressor 2. Did I miss anything? The last two are negative. Does it look good? All right. Somebody says, why don't I just calculate Q net of the cycle and then I'll know that's work net? Yeah, you can do that too. You can do that. Let's write down what is Q net for this cycle. So QB1 plus QB2, what comes into the burners? Maybe try and draw it like this at burner 1, burner 2. True. What else? And then we're going to have this down here with this heat exchanger. I'm going to show it going into the heat exchanger, and we're going to add a negative quantity there. And so this would be plus QHX for that heat exchanger. And then the intercooler. Because isn't that transferred to the environment? And so don't forget the intercooler. What do you think most people, or if you're going to forget one of them, what are you going to forget? That intercooler. I'm going to show it into the intercooler because it's negative. So this will be plus a negative QIC intercooler. All right, I pause. What about Q regenerator? Up here, this regenerator has a lot of heat transfer with it, doesn't it? But it's not to the surroundings. It's internal to the cycle. Music to my ears. That's what we call learning. So no, there's nothing like that in it. Did I get every one of them though? Do we have them all? Which one? I think we have them all, don't we? For the. Yeah, because we are specifying isentropic efficiency. That's the standard assumptions on the analysis of the compressor and the turbine. But you're right, somebody could throw you a curveball and really make it difficult. And make you go back to first principles, analyze the compressor, and there may be some stray heat transfer in that compressor to the surroundings. Nasty problem. But that's reality. All right. Okay, that's how you get part A. What is the rate of heat addition in the combustor? I should put S there, huh? Combustors. The rate of heat addition in the combustors or burners. That would be QB1 plus QB2 multiplied by M dot, and that's Q dot in the combustors into the cycle. True? Is there any other place fuel is used to heat the working fluid? Only in the combustors. So then when you get to part C, what is the thermal efficiency? Wouldn't it be, hey, what information was given is W dot net for the cycle. That was given to be 10 megawatts divided by, answer to part B, what came into the cycle in the way of heat transfer into combustors. That gives us how to solve the problem. So once we have a schematic, you would go ahead and make a temperature entropy diagram to help you in this, keep track of things. You're going to have kind of a low pressure, a high pressure, an intermediate pressure for the intercooling, an intermediate pressure for that second burner. And you would do things like this. You would start at 1, compress, cool, compress. I didn't even drop it low enough in temperature. They need to get back down to the same temperature. Then compress. Then you have the reheat, or the regenerator. And then you have the heat from the first burner. So let me throw some numbers down. State 1, state 2, state 3, state 4, state 5, state 6. So 5 to 6 is the reheat, or no, I'm sorry, the first heat in the burner. And then we expand down to 7. And then we're going to go back up to, sorry about this, I'm writing over myself, state 8, or set 7 to state 8. At the same temperature, it brings it up to the same temperature. And then we're going to expand down to state 9. And then you have some this regenerator down to state 10. And then from 10 to 1 is this heat rejection in this heat exchanger. So from 9 to 10, that's heating from, sometimes I draw it like that, saying, hey, that's what's happening with the regenerator, out of one stream into the other stream. Going from 4 to 5, increasing temperature, and from 9 to 10, decreasing temperature. Okay, look good? Challenging, isn't it? There's a TS diagram. There's the kickouts for the isentropic efficiencies for each of those states. And here's the data for this problem. So organize the information that's given. Calculate all your focus when you're using constant specific heats is the temperatures. Then make a table of all your transfers. Of the ones that students will forget, they'll forget this one right here. They'll forget that heat exchanger to close the loop, especially if it's not given in the illustration. You have to add it to make it a cycle. They'll forget maybe the intercooler heat rejection to the atmosphere. The rest of it they should do okay. You then get to make sure the net work out of the cycle is the net heat into the cycle. Then you can calculate the mass flow rate and the thermal efficiency. And I forgot to calculate Q dot in the burners, but you could calculate that. And then I calculated part C, which was not asked for, the backwork ratio. So notice that even though these have some efficiencies which are not 100%, you have some pretty high overall cycle thermal efficiency, which is great. Well, what do you want to do if you want to repeat this problem and make your life even more challenging? Variable specific heats. Can you do it with variable specific heats? Can you go into table A22 and do it with variable specific heats? Sure. You would have a piece of R for the first stage compressor, second compressor, for the first turbine, second turbine, and then modify it to get actual state 2 using the compressor efficiency, actual state 4 using the compressor efficiency. The focus is really not on the temperature, it's on the enthalpies when you're using variable specific heats. These numbers come very comparable. They're different than the constant specific heats, but energy is still conserved. And we get a more round off number of 20.00, good to 4 digits on that, kilograms per second for the mass flow rate for this problem. And there's a thermal efficiency in the backwork ratio. It does take a lot of work. So with that, we're finished with the gas turbine power plant. Let's move to another section.